Okay, hello, good morning. I am Serena Faruque, and today we'll talk about transparency, algorithmic accountability, and model interpretability. Quite a few big words. I am from SAS Institute in Belgium. Our office is in Tervuren inside a castle. And for those who are unaware, the date is October 27th, 2020. Okay, a quick summary just to make sure you're in the right place. And if you're not, let me know. The ubiquity and power of machine learning and artificial intelligence brings with it concern over negative consequences. This is something that we see in the news all the time. If it's whether it's Terminator or scandals or things where people feel there's an invasion of privacy. And one of the emerging issues is algorithmic bias. So today, through some real-world examples, we'll discuss this form of bias, some potential root causes, and then we'll eventually touch on some business and regulatory developments in this space. Next, we're going to look at some frameworks that kind of ways that I think about it and the ways we think about it at SAS for building algorithmic transparency and accountability. And in particular, we focus on how the democratization of artificial intelligence can be facilitated by using tools from interpreting models. Okay, so I noticed I've thrown a ton of stuff at you, and I would like to make it clear that you should feel free to ask questions. I can see them in a chat. So whatever you type in the YouTube box, I can see it. And Isham will let me know if something comes up or if I've accidentally blown past something. The way to think about something like this is that, yes, the mathematical tools kind of are what they are, but for a lot of the ethical or judgment call situations, it's best to have a discussion. So I would prefer that if you have questions or you have something to say, just go ahead and say it. It's, we all win by kind of understanding more. This is not something where I have the final answer. And I don't want this to be completely me just kind of talking my opinion at you. Okay, so on that topic, as mentioned, I'm a data science customer advisor at SAS, and I'm based in Tervuren. I am very enthusiastic about analytics. I am also very enthusiastic about having other people learn about these things that I'm excited about, and also have people kind of know what they are. I guess that makes me an evangelist. And these are really powerful tools to make things more efficient, more productive, and more healthy and more equitable if we use it right. So my initial training was in electrical engineering and physics, and my graduate work at Stanford focused on optimizing solar cells. Since then, I kind of moved to more healthcare related or public service related things. And so I've worked in problems in maternal health, global health, and neuroscience. And I also taught and developed courses in statistics and machine learning because I am excited about this and about teaching it and making sure people know about it. Currently, I kind of still teach things. I kind of still do research. I advise clients on the applications of data science and AI using SAS's tools. As will become important, I'm a singer, I love art, and I'm a very proud mother. So, one of the things that's kind of, one of the things looking at my background is that it's been a bit of a transition, right? So I started out in academia and now I'm working in a company. And with that comes a brand new laptop and a brand new work laptop. So for those of you who are in academia, I think we're kind of still used to using one laptop to do everything. I think once you kind of have the corporate world, you have a work laptop, you do your work only on that laptop, and then you have your other laptop and you do only fun stuff. So basically I have like my Apple computer that I do online shopping. I Google like questions late at night, like, what should I do about dry skin, etc. And then I have my work laptop, pretty new. And that one I'll be like, okay, here, download package for, I don't know, neural networks or whatever. So I've been pretty good in this new job about having one laptop for play and one laptop for work. You might wonder why I'm mentioning this, but it actually does lead into the topic that we're going to talk about today, which is my work and play computers and how it plays into advertising. Okay, so on my personal computer, which I've had for a few years, I get advertisements kind of along these lines. So we have baby and kinderkleren van 0 tot 14 jaar, blah, 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 blah. Okay, interesting. So it definitely knows that I have a 2-year-old. Interestingly, it also knows the 2-year-old is a girl and may or may not know that, well, if you could see the bottom half of me, you'd realize that there's also another child on the way. And indeed, that other child is a girl. So, from this whole experience, I'm like, well, do we need ultrasounds in a world with Google advertising? And the other thing that I found interesting, and this is, so at the time I put together these slides, I hadn't bought it yet, but since then I have bought 2 AutoStool from Orchestra. So clearly they know my buying preferences quite well, and they know what is kind of missing from my life. Now, so far, we've just mentioned that, okay, targeted advertising can be kind of invasive. They clearly can see things like inside my body that are quite private. But why are we mentioning this in the context of algorithmic bias? And in that case, we need to look at the ads on my work computer. So I just for reference, I'm still quite new to Belgium and I don't understand French that well. And from my work computer, I learned what the word célibataire meant. Apparently, on a computer where I basically do data science and data science only, the advertising algorithms have come to the conclusion that I am a young single man. And there we have like 40,000 femmes célibataires. And and basically like this was part of why I was like, interesting. Clearly my computer or these algorithms that Google uses associates work in data science with being a man. So, of course, this so far is completely hypothetical, it's anecdotal. Maybe I'm just making up stuff. Maybe I just happened to see 2 ads that confirmed suspicions I had. But indeed, there was recently a study a few years ago from Princeton where they used a very popular unsupervised learning algorithm. I think most people who do NLP end up using GLOVE. And it's a algorithm for obtaining vector distances between words. And that sounds very abstract, but it basically means that it figures out how similar and related words are to each other. And if they're more similar, then they're basically closer together. Okay. And then often, so this is an algorithm in itself. And then usually when you use this to do something in NLP, you train it on a very large data set to kind of figure out which words are close to which. And in this case, they basically scraped the internet or a big chunk of the internet. They had 850 billion words, separate words, not necessarily. And they trained it. Okay. And then to basically study bias, they tested distances between selected groups of words. So here you have a group like male, man, and here you have programmer, engineer, scientist. Here you have something like female and woman, and words like nurse, teacher, and librarian. Now, what obviously this glove algorithm has given us kind of the distance between these words. And indeed, they found that the group of words programmer, engineer, scientist is closer to man, and the group of words female and woman tend to be closer to nurse, teacher, librarian. So this is actually not in my head. The algorithms that we use for advertising do indeed associate engineering with masculinity. Similarly, they also found that arts words were closer to girl and woman, science and math words were closer to boy and man. Female names were associated with basically parenthood, marriage. Male names were associated more with career-related words like professional and salary. So indeed, this is not just one weird thing I have with my computers. It actually does seem to be something that's systemically comes out of these algorithms that people use. Okay. Now, on a more serious level, I think a lot of you may have heard of this. Amazon had an AI hiring algorithm, and they basically had an automated algorithm to rank CVs for hiring purposes. And they basically fed in 10 years of accumulated CVs, and they kind of obviously like trained on which ones were eventually hired, which ones were successful, et cetera, et cetera. And the problem is this is from mainly male applicants, and the employees in the end are also mostly male. Surprise, surprise. The algorithms ended up penalizing CVs from women. It penalized any mention that you're a woman or that you participated in a women's group. They obviously realized this is not okay, and they patched an algorithm. And it's very clear that in this case, there was a strong bias in the data, that it was basically recreating biases from humans, biases that we do not want to repeat. And so we have a question about how to address something like this. One of the things that was particularly unfortunate was that people found that this was a problem only once the product was actually in use. It wasn't, this actually was not found, unfortunately was not found at the test phase. It was used in the real world. Thankfully, I think once Amazon found out this, it was immediately pulled. Okay. And finally, on an even more life-altering course, we can discuss this thing, a program called COMPASS, which is Correctional Offender Management Profiling for Alternative Sanctions. So this is kind of complicated and hard to understand, but ultimately it's a machine learning tool for assessing risk and suggesting sentences for people who are charged with various crimes in the US. And it's based on questionnaires and on past training sets. Okay. And this actually was used. And it basically suggests what type of sentence you should receive, whether you're on bail, what type of probation situation you have. So it's like, we're like talking life-altering, life and death situations. I mean, did not do actual death penalty, but still, extremely serious things that were automated. And ProPublica, which is kind of a progressive newspaper, went through the results of what this algorithm had been doing, and it turned out that Black offenders were assessed as much higher risk than white ones, and which is, that's not okay at all. And this immediately became a really big issue in the market and in the news. And so it's obviously a form of deep-rooted racism in the training data. So here in one particular case, we have a person named Vernon Prater and a woman named Brisha Borden. They have fairly similar profiles, and you could probably argue that the Black woman actually has more benign issues. But as it turned out, it ranked the white man as low risk and the Black woman as high risk. And indeed, this was eventually reflected in what they were charged with and what they were sentenced with. Obviously, this is not the intention of the people who made Compass, and they did actually kind of try to analyze their own model. They tried to explain why their things work this way, and it's basically been a ongoing controversy because to some extent we just don't know what we think is an issue with what we don't really know how to rank what is biased and what is not and what is fair. It's an extremely complicated discussion. So this, like many other things, there's no answer. There is definitely something very, 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 very worrisome that is affecting people at an extremely fundamental level. And I think as engineers, the best we can do is let's try to think of a way to analyze this systematically. So in particular, we call this problem algorithmic bias. And we use Wikipedia's definition, which tends to be the standard. An algorithmic bias describes systematic and repeatable errors in a computer system that creates unfair outcomes, such as privileging one arbitrary group over others. Now, bias can emerge due to many factors, and in the case studies that we looked at, it seems like there were several different decisions that kind of led to a flawed algorithm or a skewed algorithm coming into use. And to some extent, it may be the design of the algorithm or the way the data is coded or collected or selected or used to train, or kind of the problem may even be how it's deployed and what choices were made in the whole process, whether things were checked. Algorithmic bias is found across platforms, and it can be limited to search engine results, social media, obviously things like hiring and sentencing, and it can be a privacy violation. So obviously I am talking about it, but something as private as a pregnancy, or it can reinforce biases about race or gender or sexuality or ethnicity. And so we are basically worried about the systematic and unfair parts. I know that there may be a case by case thing, but we're kind of worried about the things that are systematic and on a statistical level. And this is something that I think we have only thought about fairly recently. And generally the main thing that's kind of the voice of conscience has been GDPR, as controversial as it is. So we don't really have, we're just beginning to build a framework to understand this, okay? So as a data scientist, as a scientist, as a statistician, we don't want to end up in the situation like Northpoint, which is the company that made Compass, where there is an issue, you're not able to explain whether or not, your product is immoral, whether your product discriminates, whether, we want to make our work as transparent and explainable as possible. So we want to know if we have an issue, and we want to know how to mitigate this. And so it's important to kind of take a step back, think about the words of Ian Malcolm. Your scientists were so preoccupied with whether or not they could that they didn't stop to think if they should. So ultimately, we want to kind of take a step back once we've kind of made something and think about, okay, should we do this? And let's try to think of a systematic way, of a framework to kind of go through this and figure out if we have made something that we should have made and whether it's kind of safe for the world. Okay, so we can, I'm European right now, and I think most of us are in Europe or somehow affiliated with Europe. And so we can use the EU's ethics guidelines for trustworthy AI. Again, as mentioned, this is kind of like a starting point. And their 7 points are that there should be some human agency and oversight. So we don't want to kind of let very critical decisions be made only by an algorithm without having a human kind of check on it. We want to make sure that our systems are technically robust and safe, so that they're secure, that they're robust, unhackable, that they actually work as you think they are not bugs, etc. And similarly, it's kind of related. We want to make sure that the data is private, the data is governed, that we're only using data that we have permission to use, and we are not doing things to it that we do not have permission to do. We want things to be as transparent as possible, which is especially difficult with machine learning. We want to promote diversity, non-discrimination, and fairness. Should be pretty clear why. Similarly, environmental and social well-being, we want to have some form of accountability. So yeah, I know some of these things kind of sound redundant, but the point is that this is a way, like 7 things you can kind of think about systematically, like, okay, does this apply to this thing that I've just made that I'm really excited about, etc. Right? And maybe a way to like break it down further is to think about it in terms of the analytics lifecycle. So here this is kind of the way we think about it at SAS. There are many different versions of this, but they all ultimately are the same process. We start by preparing some data. So if you can see here, we prepare data, we get some data, clean it up, etc. We probably want to go through some exploration phase to understand what's in the data. Ultimately, as data scientists, we do need to build a model at some point. So once we understand what's in the data, we build some model that extracts some information, some conclusions from the data. Once we have a model we're happy with, we kind of publish it, we document it. At some point, we deploy it. And I think this is where, like, often we think about 1, 2, 3, 4, 5, these 5 steps, but then it does actually, like a good data scientist will make this kind of a circular process. You do need to monitor the that it is indeed working as you think, you need to retrain. And then eventually, from our model, we will obtain some rules. So like we can make some rules, and these things will translate into some decisions. So they can be business decisions or social decisions or personal decisions at some point. And they translate to some concrete actions, and these actions have results. And then presumably you do want to be aware of the rightmost loop, and think about what, monitor what actions and results we are getting from our system, and retrain, remodel, etc. as needed. Okay. So if you want to say about how ethics fits into the analytic life cycle, we can see that, okay, we can ask questions. Where does the data come from? Is it sensitive? Can we use it? For what purpose? Is it, and kind of in the prepare/explore area, is it fit for the purpose? Do we have reasons to think that it's biased? Do we have reasons to think that it's representative, right? Like if we're looking at Amazon data, Amazon hiring data, do we have reason to think that there may have been bias in the training set? And I think the idea is to think about it at this stage when you take the data, rather than have some problems come down, down the line, and kind of you have to start again from scratch. Okay. One of the other things I think, and this ends up, it's kind of subtle, is yes, we don't want to be used, like we don't want sex to be a hiring data. But as you saw from the advertising thing, it is possible to figure out fairly personal information implicitly. So we want to make sure that we aren't, not only are we not using the things we shouldn't be, we are not also succeeding in implicitly figuring out things. So that in, for example, like clearly Google advertisement has figured out that I am female and that my daughter and daughter-to-be are also female, without directly collecting that information. So we want to make sure that we're not implicitly using things we shouldn't be. And then this part can we explain how the model is working? Is there some bias in the model itself? Then we kind of publish the model. Once we deploy it, is it being used as intended? And I think this is actually showed up in our case studies, because once it, like in both cases, I think that there was also kind of an issue of not really deploying before testing. And then our unbiased inputs becoming biased. So somehow over time, are we developing biases in our algorithms? And similarly, like as we retrain, are the, like the neural networks or whatever we have going on, are they somehow becoming biased or unethical? And then finally, when we're going to the rules and decisions and then concrete actions and results, are the rules fair and ethical? So like this would be the hiring decision and question. And can we explain our decisions? And that I think kind of feeds into, can we explain how the model's working? And then finally, once we're like dealing with the concrete actions and results, are we ultimately doing ethical things? So especially kind of as math engineer type people, for the rest of the talk, I'm going to talk about, can we explain how the model is working, what bias is involved, and because to some extent, the rest of these are judgment things. They're things that I would love to talk about now, but as a math person, that's kind of where I can add a little bit more. Okay, So basically, like, now we know that we're using artificial intelligence more and more. It's becoming democratized. And to some extent, what will happen and is happening is that not the people who are using artificial intelligence or having things being affected by artificial intelligence are not people who necessarily understand the details of something like a neural network and whatever, like what makes a convolutional neural network convolutional, et cetera, right? I think that the percentage of people who will understand this will kind of drop, but there will be more and more people using artificial intelligence to do things. And so we want to see if we have tools to explain how the model is working and what variables are important to the model. And this helps us find out if there is bias. So one reason that this is important is that as we tend to find that there's an interpretability and accuracy trade-off. So just like without using interpretability tools, right? Something like linear regression is kind of limited in what it can achieve, but it's very clear what it means. Like there are these coefficients, if it's big, it means that that thing is important. If it's small, it means it's unimportant. If it's negative, it means that that thing, like less of that thing leads to more of another thing, et cetera, right? So that's like super clear. Whereas if you go all the way to something like neural networks, you basically have created a network of things and there are a ton of different coefficients. It's very hard to understand what one particular coefficient means. So we want to have some sort of tool so that we can use something like a neural network, which can do things that regression, like well past what regression can do. Like, you can recognize like faces of animals, which even people have problems with. But it can be sometimes really, really hard to understand like what these coefficients and connections mean. So along those lines, so we can kind of start with a really simple model interpretability tool, which is partial dependence, and it's extremely intuitive. It basically explains the marginal effect that one or two features have on the predicted outcome. So you basically plot the outcome. So it can either be like a class, a yes or no thing, or it can be a numerical value that your algorithm is calculating. And if you want to see, and you take a particular feature and you basically like show the entire range, and you show that, okay, this is what the outcome would be given a predicted outcome. And this is an extremely powerful tool to look at bias, because you can just take your model and you can look at outcome, say, versus age. And, if you have like between, say, zero, hopefully not zero, let's say like between 18 and 75, and you realize that, okay, we're actually trying to hire people only of a certain age, and that ends up being something that's important in the model, it's time to ask questions. So this actually looks at the outcome in general. Another way to look at this is an individual conditional expectation, which is you look at each observation. So they're like, different, the model is predicting different things for different observations. And you take one variable and you see how the different observations would change with that variable. So it's kind of disaggregated, but more or less the same thing. And they both kind of help you look at like, okay, if we have a variable that's sensitive, how is it affecting the outcome? And that's really, really important in understanding bias. So here we can see like how temperature affects something, how humidity affects something. You can look at age, you can look at sex, etc. Okay, so this is like one thing, it's kind of, you're just looking at the marginal, like seeing how the outcome changes if you change the input. So it's kind of just like turning the knob and seeing what happens. Okay, So like a little bit more abstract is the LIME method. So it's called local model agnostic explanation. So they're explanations that have nothing to do with the model itself. And we basically do this by fitting a linear regression model around a row. Okay. So let me make sure I'm not going over. So in particular, if we have two people, as it turns out, two women in data science, we can look at what features predict that a particular person is a particular, like that Veronique is Veronique, Jamie is Jamie. So in this case, like the ponytail is important, the glasses are not important because they both have glasses, etc. This one you can't tell what's going on, etc. And it might be a little bit more clear if you have something like picture of a frog, you do the LIME model on it, and it turns out that you identify the tree frogginess by these features in its face. So if you look at the explanation, it tells you that if you're trying to figure out what a tree frog is, you kind of look at the area around its mouth and throat area. Okay, so this is basically like, it's a little bit more abstract. You're basically explaining what goes into an individual prediction, but you're not actually explaining what the prediction will be. You're just figuring out what explains it and what explains it more and what does less. Shapley values are very similar, that they determine the relative importance of each variable to a given observation's prediction. It is not a regression model though, but they're, as you can expect, quite similar. And it's a little bit more mathematically abstract, but it's the same idea in general. We have many other tools that basically help you explain like what is important, either by ranking it or by finding some sort of coefficient, or actually seeing how the output varies depending on the input. And one way to kind of think about how to like process all of this is to think of these tools as local versus global. Okay, so local means that you're explaining one data point. Global means that you're explaining all the data points. Or you can think of them as model specific versus model agnostic. So something's kind of like, when you have something like a neural network layer visualization, it obviously explains neural networks. Or if you have something like XGBoost feature importances, it's explaining what is going on if you use the XGBoost model. Whereas if you have something like Shapley values, right, you're just explaining, it does not, you can use the model, the tool regardless of what type of model you're using. So this is one way when you like, there are many model interpretability tools. This helps you figure out what tool you want to use to get to solve your particular problem. Now, I know that we're kind of running over time, but I want to squeeze in one more thing, which is yet another tool. And this is class maximization, okay? So the way you define it, it is extremely confusing. Like the way you say it, it comes out sounding confusing no matter what you say, which is class maximization finds the member of a class that would cause the class value of the classifier to be maximized in the output. And then, of course, you're like, what does this mean? And it basically means it's the Platonic ideal of the class. So that in that class, you're basically using mathematical tools to find like the most extreme form of that class. So it's kind of like the Platonic ideal of the class. So here you can see like, these are basically the punching baggiest punching bag, or the most monastery that's possible, okay? So it can definitely help you find things. And one way that it came into action, and it actually kind of ties back into our initial concerns, is the study by researchers at Google, where it's called Building High-Level Features Using Large-Scale Unsupervised Learning. And it's really cool because what they did is they collected an immense data set created from YouTube frames, and then they created a neural network to classify those pictures. So it was completely unsupervised, so they didn't have labels on things. They're just like, hey, here's a ton of pictures, classify them. And sooner or later, the machine did its thing. A lot of the crank got turned, and we ended up with a bunch of classes. And to understand the classes, we used class maximization to understand, okay, what do this thing that this very black box, very complicated algorithm that people have worked for years on, to understand what these classes are, we just apply class maximization. Okay. And as it turned out, the most common classes were probably expected, and they bring up the issues that we bring up, plus it's kind of funny. So the most common class was exemplified by this image, okay? And it's something that they called human, but we actually realize it's a man and actually a white man. And that is the most common class. So this has basically decided this is the most common thing on the internet. Just something to think about. A bunch of the things that were in the next most common classes were human body parts, which isn't that interesting. And then it's actually kind of hard to make sense of those pictures because they just look like shadowy human parts. The next most common thing, and you should absolutely expect this, was cats. So it's kind of hard to see the cattiness of this. I don't know if you can see it, but the most common thing after humans and human parts was a cat face. So basically this is kind of what is expected. It's kind of funny, but it's also kind of something to think about. Okay, if we're taking all of the images off the internet, we basically conclude that a human is a white man, which we need to kind of rethink, like, okay, are these actually a classification that's fair and sensible? Okay. And then, so I think that we can go far more into this detail, but I guess right now, to wrap up, why should we think about this? And so far, I've kind of pushed the idea of, okay, we should do this as a good, moral, ethical person. It's kind of like very much like be a good person and be a responsible person. And that's important, sure. But I would also argue that this is also important just in terms of curiosity as a scientist, that you want to really interpret your models, you really want to break down each step of the data collection or the rulemaking or every other part in between, just because as a scientist, you should understand your model very profoundly. And similarly, I think from like the other half of my background, as an engineer, you want to be thorough. You don't want there to be like kind of a part of your product or a part of your model that you can't explain. So it's kind of both like a curiosity and a thoroughness part. As a business person, you don't want to, like apart from not wanting to make something that is potentially unfair or harmful, you want to make a good product because a good product is what sells. And so this really contributes to creating a robust product. And finally, on a much higher level, you actually don't want, in the interest of not ending up on the wrong end of compass, you want to be on the right side of regulation and legality. And to some extent, this has historically been the Wild West. We already have GDPR in place. We already have national regulations in place. And we are basically coming up with more things. And it's really important to understand the idea of algorithmic bias and the idea of how that applies to your work to understand how public policy is going to affect what you do, and it kind of makes you a informed voter. Okay, so basically this is my argument for why we should think about this, even though we're often just very much math people or data people, like why we should step back and think about the big picture. And so the conclusion, overall conclusion that from all of this is machine learning is ubiquitous. It's becoming more ubiquitous. With it, algorithmic bias is an emerging issue. We can do systematic data science. We can kind of break down our process systematically and ask questions and look for problems systematically, and can help unearth problems before they actually start, going into the real life. Model interpretability tools are particularly useful in this quest. There are many of them. There are ways to classify them. There are ways to pick the ones that are right for you. And I know that so far I've said, oh, you need to do all of this and you need to all do this. But the overall message is, look, there's so much we can do with data science. Let's just go forth and do it. And we now also have we're backed up by a bunch of tools that are important in finding out potential problems with our work. Okay, and with that, thank you. Thank you, Isham, for facilitating this, and also Arun and Roel. And if you have questions, please let me know. Questions? Okay. Okay, so I see questions from Artur, and it says, can you give an example of an organization which is kind of a role model for bringing transparency and accountability into practice? So as Europeans, I think both as Europeans and also all over the world, to some extent, the EU has been a leader in asking questions and kind of instituting some sort of guidelines and regulations and laws around building transparency and accountability. We already have GDPR, and regardless of what people think about its details, it is basically kind of the vanguard of trying to solve this. And right now, I think as some people may know, the EU is actually at work on a more kind of specific and concrete set of rules. I think it's supposed to be announced around January, which talks about more specific and concrete rules with regard to kind of ethics in data science, ethics about what model, what is understandable to people outside our field, what exactly constitutes fairness, because I think these things were things that were brought up by GDPR and kind of brought up in the European conversation, but to some extent they're not necessarily very clear, and so it's an attempt to kind of continue that process. Any other questions? Okay, cool. With that, again, thank you again for your time. Please let me know if you do think of their questions. I'm happy to talk about this, about what we're doing at SAS, and kind of my path as a data scientist offline if you'd like. And thank you, everyone. Thank you, Isham, Arun, Roel, and the whole crew. Thank you. Bye.